Okay. Today, what we'll do is I wanted to just mention a couple more things about the projectile problem on the quiz. A couple of you did calculations differently than the way I approached it. And I want to try one more time here and see if this will show up. That's not really acceptable. So.
There's a button you can hit to like readjust the light or something.
Light. Let's see.
I can see it.
Yeah. Okay, well let's just, I think that's reasonably legible. That's okay. So on the quiz, what we had is a projectile that was arcing up and over with an initial speed of 500 meters per second and at a liftoff angle of 60 degrees. And I'm just simply saying that again for the recording purposes. One part of the question then was asking what the acceleration is at 30 seconds. So what we had to do is we needed to figure out what the angle was that the projectile was at 30 seconds. Well, that calculation turns out to be 48 degrees because you need the X reading and the Y reading. Most of you had that just fine. And then that angle is what sits right here. And then beta would be a complementary angle from the vertical. Now, to find the acceleration at 30 seconds, we know that the acceleration of the projectile in free flight is 9.81 directed downward. So this complementary angle beta, it's real simple. If you drew this picture, people that had trouble did all kinds of weird things with dot products and other kinds of more sophisticated approaches, trying to figure out the different components that make up AR and A theta. That was not necessary. If you use beta right here, you can see you take G cosine beta, and that'll be equal to AR. And that calculation is right here. And notice that you have to assign a negative to it because you can see the positive sense of R, and you can see that AR opposes that. Similarly, A theta opposes the direction of the unit vector theta hat. So we do those calculations, and they're right here. That beta angle is the complementary angle, as I said. And so here's the calculation for the R term and the theta term of the acceleration. Also, several of you where you had mistakes in here, what you should do is look at this and realize that the magnitude of this thing has to match 9.81. Is everybody clear on that? The acceleration is 9.81, period. So no matter what coordinate system you use, it's got to be 9.81 on the magnitude. So you should get values here. Some of you had values that were like, 12, 14, something like that on one of these components, and so you should have been clued in right away that something was fishy. If we flip the page and look at the acceleration in the normal tangential approach, see how that shows up. That's pretty decent. You'll notice that tangent to the velocity has to be obviously always in the tangential direction, and this angle that the velocity is at was easily arrived at from the x component of the velocity and the y component of the velocity. So knowing that, then this angle right in here related to g must be that angle. So again, you just decompose this into a normal. A couple of you had the normal pointing the wrong direction. The unit normal always goes what direction? Always towards the center of curvature. Doesn't go outward.
Can you put an arbitrary direction and hope a negative sign will direct that component?
Well, why don't we just all live consistently is what I would encourage you to do. Okay, because, I mean, otherwise, I mean, you can do that, but then you got to be aware of something, and you're trying to do something in a different way than the way that you want to try to be consistent in the work that you do. You could do it a different way. And if you did something differently and I didn't quite catch it in your work, feel free to get in touch with me and I'll look over your work and give you credit if I didn't understand something that was in your paper. Yeah.
I want to answer this maybe after class or something. But when you're at an inflection point, where does end point?
Excuse me?
If you're at an inflection point, where does end? There's no concavity for end to.
That's right.
have a
Well,
direction.
there's no normal acceleration there either.
Right.
There would be no normal acceleration at a inflection point.
So I was just thinking, if you use it as a coordinate system, then there's no direction.
Well, it always has to be towards the center of curvature. And if you go back to the derivation we did it in polar and we did it in normal tangential. If you go back to those derivations where we used little unit vectors that were in the tangential direction, and then we allowed a slight rotation a slight motion to occur, then that set a new direction for the tangency, unit tangent, and then we had a differential that was on the outer edge of that has to point in the direction of the inside of the curve. It wouldn't exist if the object was at an inflection point. It just wouldn't exist. Okay. And it flip-flops when you go through an inflection, right? It's going to go, the normal is going to go, as it transitions through that inflection spot, it's going to go from pointing one direction to pointing the opposite direction, right as it transitions there. And also, near of an inflection point, what about the radius of curvature? As you approach in the limit, near an inflection point. Near an inflection point, as you're coming in, here's your inflection point. As you're coming in here versus coming in here, what's the radius of curvature approaching? In here, you might have a radius of curvature like this. As you get close to that inflection, what about the radius of curvature? Still concave down here.
But it's going to be longer.
Huh?
Q goes with infinity because
Yeah.
AN equals the V squared over rho, and if there's no AN, then rho has to be infinity.
Correct. That's exactly right. As you approach this inflection point, there's no normal acceleration. There's no normal acceleration there, which means the radius of curvature has to become infinite. The thing's transitioning from, it almost becomes right. You can think of it as becoming straight there. Keep in mind what a radius of curvature is. It's matching, like over here, it's matching a circular circle of a given radius at that particular point. It's matching the curvature right there at that point. And that radius of curvature changes as the curve shape changes. And that radius gets greater and greater and greater as you approach an inflection point. Then you go past that, and it becomes infinite the other way, and then tightens down to be something finite. Okay? So the idea of, back to that picture, this was the easiest way to go about finding the components. A couple of you used, let's see, who was it that remembered, what was it, R prime dot with R double prime? Jake did. There's something in your calculus book, Anton Calculus, and he came out sweating afterwards wondering, well, I wasn't sure if he remembered how to do that correctly, but there's a magnitude of a dot product divided by, what was it? Do you remember?
Yeah, it's the magnitude of the R derivative cube.
The cube of the first derivative?
Yeah.
Yeah. So it's R prime dotted with R double prime, I believe, magnitude.
Mm-hmm.
And then it's divided by R prime's cube. Something like that. You can find it in your calculus book. So you remember that. And one thing that was interesting, I didn't see anybody try to figure out the radius of curvature. Oh, where was that calculation? It's sitting right here. Actually, it's sitting right here. Here it is. This was the easy way to do it, which is the way just about everybody except Jake did it. Okay. And that's 9.5 kilometers. That's a pretty large radius of curvature. But, and of course, this projectile, even as I mentioned in the statement of the problem, 500 meters a second is fast. That's half a kilometer per second. That's a major projectile, okay? And so this thing's got 30 seconds. It hasn't even reached the top of its flight path yet. And I told you that in the wording. A couple people that got in trouble on the quiz didn't draw sketches. If you draw sketches, that's going to give you that insight. So I highly recommend that. Don't just rely on a page of math. Okay. Is there anything else? Oh, what I was looking for, what I was expecting somebody to do here to figure out this radius of curvature was to come up with the equation of that parabolic path. Y is a function of x. And then remember the thing that I did with you a couple weeks ago where I can't remember at the moment what it is. It's always in the back of our books, though. You just look it up where you have y as a function of x, and you form the radius of curvature that way. Alfred?
Isn't that exactly what you did with the vector thing, except you just say y as a function of, like you basically just say x is going to be some constant times t, and then other stuff happens that makes it reduce to that.
Well, it's more of an algebraic approach to get it, as opposed to having to do the vector calculations. Let me see if I can find that here quickly. I cited this for you back when we talked about this previously, but nobody did that on the exam.
Page 700 or something like that.
That sounds pretty good to me.
Yeah, it's on page 7.
There it is. Yes. Thank you. And this is the thing I happen to have remembered. Given a function, given a description of a path, y is a function of x, you just create this representation for it. Okay?
That's nice.
And so it works out, that would work out just as well. And I've given quizzes similar to this previously, and there's usually somebody in class that'll do that, take that approach. Okay, so if you got a low score, don't be too discouraged. Just come see me, work with me. I'm here to help you be successful in the course. So want to make sure you get your math skills down so you're feeling really good about that when you make the transition to the university next year. And then also, of course, your graphics and being able to problem solve. That's what this is all about, is getting your ability and your confidence up to be able to handle problems that come at you where you aren't sure what way to tackle it, and you just start fiddling and work your way into it. Okay, any questions on the quiz? Come see me if you have a discrepancy on the scoring. I won't grade you down. I might grade you up. Okay. Okay. All right. Okay. So what I'd like to do today is to go ahead and work more problems with you in curvilinear motion. And I'd like to give you some insight into some of your homework problems that have been assigned. So what I'm going to do is flip through pages of the book and give you a little, some answers to some of the problems that did not have answers provided. And let's just go back to the beginning of chapter 3, and I'll look through the assigned problems. And see if there's something that was assigned that didn't have an answer provided.
16.
Excuse me?
316.
Number 16?
Yeah.
Okay, thank you. Here's number 16 on page 133. I'll bring that in a little more. It's a nice problem. Small package deposited on a conveyor belt right here. Gets dropped on there with 0.8 meters per second. And then it's sliding down this, and what we want, well, the coefficient of friction is 0.3, so it slides down here and arrives here at B, and then goes on to the same friction surface and slides out here and comes to rest. So we want to calculate the distance that it'll slide out there. So that'd be a reasonable manufacturing kind of problem, and then what you'd do is you'd probably either have a robotic arm here at location C, or you'd have a human being standing there. This object comes sliding right up to them. They just reach out there and pick it up and put it over where it's supposed to go from there. So here are the answers. The velocity of B is 3.17 meters per second, and the sliding distance is 1.71 meters.
Yeah, or was it just the distance, or did you?
I think you just had to find the distance.
Just the sliding distance was required there.
You have one to get the other, but.
Yeah, you needed that intermediate value, didn't you?
In order to get
Yeah.
Yes.
If you saw it through that, if you saw it through like this, yes.
Yeah. If you now there's a way that we'll be learning. We'll start introducing that this week. Is using work and energy. We'd be able to solve that problem very simply. Okay. And then let's see. Any others coming up here? I'm looking through the ones that are assigned.
So which homeworks do you want done before the exam? 11?
I'll tell you about that in a minute.
Can you also go over the answers for 218 in chapter 2?
Okay, hold on a minute. Let me stick here in chapter 3 for a second, since that's where I'm at. I want to show you something that it was assigned to you that Ian was asking me about earlier today. And it's this question right here. Number 47. So we spent quite a bit of time the other day on a chain that was on a horizontal surface. It transitioned from a smooth surface onto a rough surface. And the mathematics in that problem are similar to this problem. Now, most of you probably haven't gotten to this one yet. Is that true? Have not gotten to it?
I've looked at it and found several wrong ways to do it.
Okay, good. Daniel found several wrong ways to go at it. Okay, the first part of this that you have to think about, and I didn't get a time to talk to you earlier today, Ian, about it, is you need to figure out how much chain has to hang over the edge to get this thing starting to move. Okay, that's a starting point. So you have to figure out how much chain needs to be hanging over the edge first to get it starting to move, which means that the weight of this hanging piece of length B, which is the density times G times length B, that weight, that force, creates a tension. Here, see what I wrote right here, a T, little T vector? And that T vector transitions over the corner and then acts as a tension vector on this upper segment that is resting on this friction surface. Now you know that for break loose, this pulling force here, which is the weight of the piece hanging, must match the mu normal of the segment that is resting up on the rough surface. And here's the friction force, mu times its normal. And so that is the required B length necessary to cause this thing to pop loose. That force, M rho G B, must match the friction force, mu rho G L minus B. Then, the next step Yeah, I don't want to show it all to you. The next step is to use v dv equals a dx, where your integration, I'm going to go ahead and write that up on the board.